This video is on the objective complete the steps of a two-mean hypothesis test. Right, so the difference of two population means with population standard deviations unknown. Right, so we're eventually going to be using the student's t-distribution with so many degrees of freedom. And this is also the critical value approach. Right, so we're going to be finding a critical value if it's a one-tailed test in a rejection region, or two critical values in two rejection regions, if it's a two-tailed test. Finding a test statistic and determining if that test statistic falls in the rejection region or not. Using that to make a decision, do you reject the null hypothesis or not reject it? And then make a conclusion about the initial claim. So it's all the same steps as a one-mean hypothesis test. Just now you have more to worry about because it's two means, two samples, two populations. All right, so let's take a look at this question. And if you'd like to see more about what they're saying about this, click on more instruction, look at their videos, their notes, their examples, and hopefully those help you. All right. So here, a fast food franchise looking to reduce wait times for customers launched a pilot program in which customers could use a smartphone app to place orders. The accompanying table shows the data on mean wait times in seconds at 14 stores participating in the pilot program and at 14 stores not participating in the program. Assume that the mean wait times are normally distributed for both groups of stores. So let the mean wait times of the stores not in the program be the first sample. So with all the subscript of 1 that you're seeing here. And let the mean wait times of the stores in the program be the second sample. So see with all the subscripts of 2. All right, at the 10% significance level, is there evidence that there is a difference in wait times from those that use the app and those that don't use the app? All right, so we're given all this information about the sample here. All right, now first we're asked to identify the null and alternative hypotheses. All right. So I'll go to some paper. Now what we're asked to test, or what the claim is, right? It tells us, it tells us to test at this 10% significance level. Test is there evidence that there is a difference in wait times between those that use the app and those that don't use the app. So our claim here, what we're testing, a claim, belief, what we're testing, what we're investigating. Now remember, mu1, all the things with a subscript of 1 will be for people that don't use the app, that are not in the program. And then mu2, anything with a subscript of 2, will be related to those people that are in the program, that are using the app. And what we're testing here is whether or not these are different. So are these not equal to each other? Right. Now another way to state this is that mu1 minus mu2 is not 0. This is an alternate way to say that. All right, but once a claim is established, right, then you can set up those hypotheses. The null hypothesis, the alternative hypothesis, and the claim here does not involve equals, right? It is not equal. So that's going to be represented by the alternative. Mu1 is not equal to mu2, or mu1 minus mu2 is not equal to 0. And then the null and alternative hypotheses should be opposing statements, right? The opposite of is not equal to is equal to. And this is what's going to be assumed to be true. You assume that these wait times for people that don't use the app and people that use the app are the same on average. And then later on we'll decide if we want to reject that or not, right? Reject that assumption or not. Okay, and that's the first part. Now they also mention, usually after the hypotheses are formed, we identify the significance level of the test, which is 0.1 or 10% here. Another thing you can point out when you have formed the hypotheses is what kind of a test it is. We have that mu1 is not equal to mu2, or mu1 minus mu2 is not equal to 0, that these wait times on average are different. When it is not equal, remember this is a two-tailed test. So, being that this is the critical value approach, we're going to be finding two critical values, one positive, one negative, such that the area to the right of the positive one and the area to the left of the negative one add up to 10%, so they'd be 5% each, but we'll get to that in a minute. Alright, so I'll fill this first part in, take this one step at a time. The null hypothesis, we're assuming that they are equal, and the alternative, they are not equal. Is there a not equal symbol here? Keyboard comparison. Here we go. Not equal. Great. Submit. Wonderful. All right, then they'll keep us, going through step by step the steps of a hypothesis test. Right, so I'll hit continue, and it gives you it's the same question. Nothing changes. Right? It's the same question, but now we're asked to identify the degrees of freedom and the critical values to be used for this hypothesis test. Alright, it says do not round, use the exact value from this t-table. Alright. Now, notice it never said anything about assuming that the population variances, the population of people that that are not in the program and the population of people that are in the program, using the app, it didn't say anything about assuming that those population variances were equal. And it just said that you can assume that those wait times are normally distributed for both groups, but it didn't say anything about assuming that they were equal. So remember, this is the calculation of the test statistic part. Right? So I'm going to write down all this information on paper. So we take our samples, right? So we take a sample from each, and again, I'll write down this information. Not in program. This is population 1, the people not using the app, and their average wait times and stuff. And then in program, right, the people that are using the app. And the sample size for the people in the program, there are 14 of those, 14 stores, not people, but the stores. There were 14 stores that, didn't have people using the app. And then for those 14 stores, the average wait time was 287.9 seconds. And the standard deviation was, 35.4 seconds. And then for the stores that are using the program, having people use the app, 14 of them as well. That's N2. And X2 bar, right, the average wait time for these 14 stores was 244.4 seconds. Standard deviation, that's S2. Standard deviation 38.4. Now, like I said, notice that they did not assume. They did not assume that sigma 1 was equal to sigma 2, right? These are the population standard deviations. And if that's the case, we're in that non-pooled scenario, Hopefully you recall from a previous assignment there was, when you're doing these two sample t-tests, there's a scenario where you have a non-pooled scenario, you're not pooling the standard deviation, and then there's another scenario where they do assume that the population standard deviations are equal, and then you have a pooled scenario where you have to find that pooled standard deviation estimate, SP. Well, we're not doing that here. Right. And in this case, the distribution of the difference in sample means, x1 bar minus x2 bar, is a student's t distribution where the number of degrees of freedom is the smaller, in this book, just to be much more conservative, it's a very conservative use of degrees of freedom. The t distribution is the smaller value, the minimum value of n1 minus 1 and n2 minus 1. Well, in that case, this is a t distribution with 13 degrees of freedom, right? Because n1 minus 1 is 13, n2 minus 1 is also 13. The smaller of 13 and 13 is 13. So we're looking at 13 degrees of freedom. Okay. And they're asking us here to find the critical values. So if I'm looking at a t distribution with 13 degrees of freedom, and we'll get to the test statistic in a little bit. I know usually we calculate the test statistic first, but here in this they're asking us to identify the degrees of freedom, 13, and the critical values, right, because it's a two-tailed test. So I'll draw this t distribution with 13 degrees of freedom here. We got number line with t-scores, symmetrical bell-shaped curve. Underneath the peak, right, is a t-score of 0. And I mentioned already it's a two-tailed test, and alpha is 10%. Right? Two-tailed test, alpha is 10%. So I'm looking for two critical values. Right? So there's two rejection regions, one in the right tail, one in the left tail. So I'm just drawing my rejection regions right now. And both these rejection regions should add up to 10%. So that means this rejection region on the right has an area of 5%, and so does this one, so that they both add up to alpha. They both add up to 10%. So we're looking for, what's the t-score with an area of 5% above it, and then the opposite of that for our critical values. And these I can find, using a calculator or using a table, and I'm just going to use the table that they provided. So I'm in a t distribution here with 13 degrees of freedom, right? It came from this non-pooled, smaller of 13 and 13 degrees of freedom. So let's look back at that table. So degrees of freedom, 13. So I'm in this row, right? And we're looking for the t-score with 5% above it, right, which is 1.771. Right. So this score here is 1.771. So any t-score of 1.771 or greater will be in that right tail rejection region. And then this score over here is just negative, the opposite of that, right? Negative 1.771. And if our test statistic comes back as negative 1.771 or lower, it'll be in the left tail rejection region. All right, so I feel like they're going to have us calculate the test statistic next. All right, but let's fill these in. All right, so we have degrees of freedom. Again, it was the smaller non-pooled scenario, right? We didn't assume that the population standard deviations were equal. So it was just a smaller of 13 and 13, which is 13. And then the critical values, right? And it says, since there are two of them, we should use the plus or minus here, right? There are two critical values, so I use the plus or minus and then the 1.771 from that table, right? That value with 5% above it. 1.771 has 5% above it, negative 1.771 has 5% below it, making a total area of the rejection regions the 10%, which is our significance level. But don't forget the plus or minus if there are two. Now if it was a right-tailed test, you're just using one positive value. If it's a left-tailed test, you'd have to use one negative value. Hopefully you can figure out what kind of a test you're running. All right, so now I believe they're going to have us calculate the test statistic. Yes. Calculate the test statistic, and round to the nearest hundredth, which is 2 decimal places. All right, so back to my paper. All right, so if you recall, and I'll come back to this picture here. Remember, for these non-pooled scenarios where the population standard deviations are not assumed to be equal, the test statistic, since, and again, my population standard deviations are also unknown, so this is a t-score. And we're working with the student's t-distribution, 13 degrees of freedom here. So what's the t-score for the difference in our sample means? Now again, hopefully this rings a bell from a previous assignment. I'll write out the formula. Now again, this is in the non-pooled scenario. In the pooled scenario, it was different a little bit, right? I take the difference in my sample means, x1 bar minus x2 bar, minus 0, right, the assumed difference from the null hypothesis, so no need to write minus 0, divided by, and then the standard deviation of the difference in sample means, the distribution of the difference in sample means, which was the square root, and then all inside that square root was, s1 squared over n1 plus s2 squared over n2. All right, so we fill all those numbers in, right? We were given all these numbers in the samples above. So in the numerator, I've got the difference in our sample means, 287.9 minus 244.4 divided by, and then big square root, and then the first sample standard deviation squared, the first sample variance, 35.4 squared, divided by the first sample size, 14, plus, and then the second sample variance, 38.4 squared, divided by the second sample size, also 14. And I'm going to enter this into a calculator. So I pull a calculator up, and in parentheses the numerator, right? 287.9 minus the 244.4, close parentheses, that's all the numerator, divided by, and then in the denominator, the square root. Now again, make sure this entire expression down here is under the square root. So we have 35.4, that was s1 squared, divided by 14, plus, and then 38.4 s2 squared divided by n2 divided by 14 as well. Again, notice that in my calculator here, the square root bar just kept extending, so all of this is under the square root. In one of the older ones, you might have to put parentheses in the beginning and end to make sure it's all underneath. So it's about 3.116, so 3.12, all right, if I round to the nearest hundredth. All right, so our test statistic, and I'll put this on here right now. Going back to my graph of this t-distribution with 13 degrees of freedom and our rejection regions, our test statistic came back 3.12. Now where would that fall? That would fall over here. Right? 3.12 is definitely beyond 1.771, and here's the test stat. And since that's in the rejection region, we're going to reject the null hypothesis. We'll get into all that in a little bit. Right, so back here, test statistic rounded to 2 decimal places, 3.12, nearest hundredth. Okay, great, and then go through the same calculation I just did. All right, then to the now it's decision time and conclusion time. Right. So I said back on paper, let's get rid of the calculator. Our test statistic is definitely in a rejection region. So we would reject the null hypothesis. I'm going to go back to my hypotheses. All right, now the null hypothesis is what we assume. The null hypothesis claims that these wait times are equal on average for the people that don't use the app and the people that use the app. Well, we're rejecting that and saying more that this is probably more true based on these samples, that the average wait times for the people that don't use the app and the people that use the app are different. All right. So we would conclude that there's evidence to support this claim that the wait times are different. Right. So let's go back and read which one says that. So it's one of these two. All right, reject the null hypothesis. This one says there's not enough evidence to show that there's a difference in the wait times. I just said the opposite of that a second ago. I said there is enough evidence. We would support the statement that there is a difference in the wait times. So it's this statement here: reject the null hypothesis. There is enough evidence to show that there is a difference in the mean wait times between stores in or out of the program. And we're done. Okay, that is the end. Once you've reached a conclusion about the original claim, you're finished with your hypothesis test. And I believe that's the end of the problem. So, and I also think, based on how many questions were asked, that's the end of the objective. Yes, so the objective is complete. And this is similar to earlier assignments when you had the objective of completing all the steps of some hypothesis test. If you are careful and go through it and do it properly the first time, you shouldn't have to do anymore. Right? If you complete the steps of the hypothesis test, don't get anything wrong, you'll have to do just the one question and the objective will be done. Now, of course, if you're getting things wrong, it'll throw some more questions at you. It'll be a bit longer, but just be careful. Now, I wanted to point something else out to you, though. In this case, right, we did not assume that the population standard deviations were equal, so this was non-pooled, and my degrees of freedom were this. The minimum value of these two here, and the way I calculated the test statistic was this. If you recall, if there's a pooled situation, it's a little different, right? So remember, here was the pooled situation. If it's ever mentioned that they are assuming that the population standard deviations or the population variances are equal, then the t-distribution, well, then you have to calculate this SP, right, this pooled standard deviation. You have to calculate this, and then your t-distribution has n1 plus n2 minus 2. It's the sum of the sample sizes minus 2 degrees of freedom. And your test statistic is that difference of your sample means divided by, and then SP, this pooled standard deviation that I showed you the formula for a second ago, times the square root of 1 over the sample size 1 plus 1 over sample size 2. So it's a little different if they do mention that they assume that the variances, the population variances or the population standard deviations, if they assume those are equal, then you have the pooled scenario and have to calculate things a little differently. So be careful of that. Look back at an old assignment, the previous assignments for the pooled scenarios. But I'll tell you right now, most of the time you're probably going to come across non-pooled because usually you can't, if your population standard deviations are unknown, usually you can't just assume that they're equal. All right, so most of the time you're going to come across a non-pooled t-test. All right, so hopefully watching me do this, looking at the more instruction, reading the answer explanations. Hopefully all this stuff helps you out when you're working on these assignments on your own. And thank you very much for watching.